Twin I-beam is another suspension system design that you commonly see with Ford, and it kind of works like scissors. And so one of the things that one of the things you can appreciate, you can tell I kind of beat up on Ford a little bit unfairly sometimes, but every manufacturer has their merits. My family, farming and ranching, you can imagine they're hardcore Ford people. And so Ford trucks is what my family basically buys. So don't get the wrong idea from the way I phrase things sometimes. But you'll notice I don't drive Fords. But the Ford is killing everybody in the truck department. They sell more trucks. That's their bread and butter. That a Ford truck is a very solid work truck. And it's because of some of the design choices that they make like this. This design choice right here is not about comfortable ride. It's not about that aspect of it or good tire wear. If you look at this design straight out of the gate, hopefully what you're appreciating from this design and what you see is those are big freaking metal parts, are they not? It is durable. That is strong. That is a big chunk of metal. Not going to be the best for ride quality. Not going to be the best also you'll see with time and from experience for tire wear. Because it kind of scissors the tires like this, it scrubs the tires, and all of these pickups with this design have tire wear. However, this is not something that's going to break on you. There's a lot of metal on that, really solid and strong. And so for a truck, that's kind of a big deal, right? Super durable, very strong, not gonna break. Twin I-beam there. This is what you usually see in racing. This is one of the best suspension designs. This is called a 4-link suspension, or what's called a strut SLA. Variety of manufacturers use this. Toyotas and Hondas will use this. BMWs will use this because it's the best. I mentioned that in general, right, you buy a luxury car, they're going to do what is the best design, not necessarily the cheapest design to make. It's got a lot more parts than all the rest of them. But this is a very quality design for ride quality, for handling. And so this would be what you would often see in racing applications for a design. And you'll see it would, in a racing application, it becomes very adjustable. But this is a 4-link suspension or strut SLA. What's different about this, there's our strut coming through here that would attach back to the knuckle, has an upper control arm, a lower control arm, and then this would be called typically a 3rd link. And so this design, 4-link, 1, 2, 3, 4, right? The strut, the upper control arm, 3rd link, and the lower control arm, there's your 4 links. The lot of good steering geometry from this, great tire wear, great handling, great ride quality out of this. One of the things I want to point out to you too is that neither the upper control arm or the lower control arm can support the weight of the vehicle. The weight of the vehicle is where the spring is. So the strut over here supports the spring, which then attaches basically to the 3rd link at this juncture here, and then the knuckle. Weight of the car would go from the strut to the knuckle to the tire to the ground, and then this ball joint and this ball joint become followers. McPherson strut, probably one of the most common suspension designs nowadays. They're putting struts on trucks and cars. For the longest time, it was short long arm was a truck thing. And really, if I back up further, everybody used short long arm. Then struts came out and cars had struts, trucks had short long arm by and large. Then nowadays you see struts put on a lot of different stuff. But what you have, strut carries the weight of the vehicle, right? Strut, control arm, knuckle. Pretty simple design for most struts. This is called a McPherson strut design. Couple of things about that. I'm going to grab a couple pieces over here to demonstrate something. So I didn't bring with me to class today, and I regret not bringing one. But I didn't bring a strut that was broke down. But you've got your strut, the inner shock portion, and then you've got an upper mounting plate like this. So the spring can come apart separate, and the mounting plate, and then a strut by itself. So the shock portion is part of that strut housing. which you can see here what's in green. So we've got an ability to cage a strut, couple of safety aspects of this. This spring does support the weight of the vehicle. So when you take these out of the vehicle, you take them out like this as an assembly, and then we cage them and compress the spring before we would ever take a strut apart. Then you'll get your upper mounting plate off, and that upper mounting plate will have a bearing in it. So from there's a bearing on that, because this strut, when it's fixed to the knuckle, then when the wheel turns, right or left, if I turn the wheel, then I need to be able to have a movable connection, which is what that bearing supplies for me up in here. So most of the time when struts go bad, then the bearing plate is bad too, and so this is one for me that goes together. Timing belts and water pumps go together. Make sure that whenever you replace a timing belt, you're replacing a water pump with it. And then in addition to that, we'll have it with struts like this. Then if I ever replace a strut, I replace the mounting plate and bearing as well. A couple other things I've mentioned that kind of go together. When you do axle seals, you do axle bearings. When you do struts, you do the mounting plate. When you do timing belts, you do water pumps. Now, those things just kind of go together. Most of the time, you don't know what killed what, but most of the time the strut goes bad, I would say. And then it overhammers the spring and then the mounting plate, right? So when the strut and the shock portion of the strut goes bad, then it lets the spring bounce the crap out of everything, and then it hammers out the bearings. So when you get the clattering noise that you get over bumps, you get this clack, 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 clack. I told you I go for sway bar links can be common, but there's a very distinct noise that comes from a strut rattle, and that you'll pick up on the more you do this in the industry, and then it'll put you in that direction. A couple of other aspects. I can eliminate down and know it's the strut if I eliminate other noises like sway bar links and so forth. One of the tricks that I picked up on in the industry is that center bolt is holding all the tension back of the spring, and so you would never take that center bolt out unless you had the strut caged. But while it's on the car, I can usually see that center bolt. And that center bolt is being held in the center of this mounting plate by the integrity of the bearings that are there. So a lot of times when I can diagnose bad bearings and a bad upper mounting plate, and it's usually the bearings in that case, I can diagnose that that's bad by watching that center bolt while I turn the wheels lock to lock. Now, if that center bolt stays right dead center and just kind of flexes and pivots, then fine. But if I see that center bolt start to walk around in a circle as I turn the wheel lock to lock, then that's an indication that that bearing plate is no good. So that's a good little trick that you can do while this strut is still installed on the car. A couple of other things about that. This is my 2 cents on this. Everybody in the industry, all the manufacturers are going to say, put this strut together dry. So they want you to put it together dry because a lot of times at the bottom end of this strut, where the spring houses in the mounting point of the strut, there'll be a piece of natural rubber as a little bushing down there to keep metal to metal grinding while that spring kind of flexes and moves. And to keep it from wearing through, it cushions the bottom of that spring. You have the same thing in the top. The industry would say put them all together dry. Myself, if I was going back together and rebuilding this strut, I would reuse the spring, replace the strut, replace the mounting plate. Now, there's no guarantee at the end of this spring it comes over to a juncture right here, and you can see, a spring wouldn't be completely flat on the bottom. And so it comes over where the end of the spring is there, and the same is true up here at the top with this mounting plate. Now, when I take this apart and put it back together, I will do my best to get that spring and that bushing positioned exactly how it was before on the old strut. I'll get it positioned on the new. But I'm human, and it may not be exactly where it was before. Now, if it's not exactly where it was worn in before, then a lot of times you get a squeak out of it as it tries to move back and it's in a new position and it's wearing in on the old rubber that's there. So it's not okay to put petroleum products or anything on a natural rubber bushing because it'll make it deteriorate and erode away, which is why the industry says to put this stuff together completely dry. My 2 cents on that, I would put them together with disc brake caliper lube. That's a silicone-based fluid, it's not a petroleum product, and so it's not going to affect this rubber. And I would just paint on a little bit so that if I got the spring in a little bit different position, then that little bit of lubrication would allow the spring to slip back where it wants to be. And then I never had comebacks on my jobs that I did struts where the customer would bring it back a little later and complain of it squeaking. If I put a little bit of lubricant on there, disc brake caliper lube, silicone-based lubricant, not going to tear up the natural rubber, I got away with it. And so on an ASC style question, the correct answer is put it together dry. In practice, I would put a little bit of lubricant on there that would not interact with the rubber, so disc brake caliper lube or something like that. So then we get into steering. So steering fundamentals here, want to briefly cover a little bit about steering so that you can be successful in your inspections. So steering main purpose is to have directional control of that vehicle. We can turn our steering wheel. We want good steering geometry, and then we want to be able to turn our vehicles easily. There's two common styles. There's others from back in the day, but the two most prevalent styles of steering and suspension design would be parallelogram steering and rack and pinion. So this one here is rack and pinion. Rack and pinion would have a steering gear box. That steering gear box would be right over here where this pitman arm is. We've got a pitman arm and then an idler arm there. The pitman arm would connect to the steering gearbox. Steering column would come down and tie into that gearbox, pitman arm on the end of it. As I turn the steering wheel, the gearbox would drag that pitman arm back and forth, and then that pitman arm is going to drive everything else back and forth. Pitman arm and idle arm hold the weight of all the other steering components. So we've got a center link there, an inner tie rod and an outer tie rod, and then a steering arm is out here on the knuckle where the tie rod attaches to. So parallelogram has a lot of parts. Outer tie rod on both sides, inner tie rod, an adjustment sleeve in the middle that's like a big long nut that the inner and outer tie rod would thread into. Then you've got a center link there, idle arm and pitman arm. Couple of things, a lot of parts on this. Strong, durable, mostly used well, everybody used this back in the day. Then again, rack and pinion came in, rack and pinion for cars, parallelogram for trucks because it was stronger. Then nowadays pretty much everybody uses a rack and pinion on your medium heavy duty trucks, and since it's stronger they'll often still have parallelogram. Now, a couple of things I want you to understand. Pitman arm, idle arm, they're holding everything up. So they're supporting the weight of all that those steering components. In addition to that, every time the tire gets jammed and hits a pothole or something, it jams up on those, or gets jammed this way, it pulls down on them. They will be the first things to wear out. So they're holding everything up. That is one of the more common things to wear out on this is idle arm and pitman arm. All day long, you do idle arms and pitman arms. A pitman arm by itself looks like this. So there's a pitman arm all by itself. Idle arm would look similar to this. And so there's a pitman arm there. It's going to wear out all day long because it supports the weight of the vehicle. When you take this off of a gearbox, there usually is a press that comes over and hooks like this, and then a bolt that drives on the shaft that runs through the middle of this, and you can press this off. Get creative in your mind on stuff like this. This one in particular, if I were to pass it around the class, you would see that I've got a big cut out of the side of this where I had to cut this one off and weaken it. We cut it with a buzz wheel and hit it with a chisel to chip it off of there so that we could get this off of one of the students' cars because it would not come off. And so get creative. Not something you can really put heat onto because you'd ruin the seals on the rack and pinion, but I cut it with a buzz wheel to weaken it. I don't care about this one. I'm throwing it in the trash anyways. But get creative on sometimes you have to work outside of the norm to be able to get some of these jobs done, because I'm certainly not sending a car out of the shop and saying, well, I can't get that part off, right? I'm not doing that sort of stuff. I'm going to find a way to get it done. You get to use your mind and get creative and figure out how to get things apart. Pitman arm, idle arm, center link, inner tie rod, outer tie rod, adjustment sleeve in the middle, and then the little part in red over here is called a steering arm. That is all parallelogram steering. Parallelogram steering systems use a gearbox, where rack and pinion uses a steering rack. And so you can see on this design why it took over. This is a lot simpler. What we have in a design like this, here's rack and pinion, all you have is a steering rack. The steering rack right here is the equivalent to your gearbox on your parallelogram. And then on the end of these steering racks, what you have here is just a tie rod like this. So really the only steering components that are here is just the rack and then tie rods. You've got an inner tie rod and an outer tie rod. So the inner tie rod, these can separate. An inner tie rod by itself would look like this. There's an inner tie rod, and then this portion out here is your outer tie rod, and it's got the boot all torn off of it, but there's an outer tie rod there, and then it's got a lock nut for safety. And once you thread this on and you set the length that it's supposed to be during an alignment, then you lock the nut down so that nothing can move, and then everything's jammed in place. The rack and pinion steering is very simple. You got a pinion gear that's circular there, and it just sits on a rack of teeth. And then as we turn the pinion gear, it drags a rack of teeth over this way, drags a rack of teeth back the other way. And so what you see on these, there's a big rack of teeth on the inside that tube. And so as I turn it this way, this side's getting shorter and that side's getting longer. All right. Very, very simple design. So as I turn it back the other way, this side gets shorter and now that side gets longer. And so it's a super simple steering design. Less parts to break, because it has less parts involved, and so then it makes it more reliable. You can see why manufacturers would start to switch over to this design. So power steering systems, a couple of different varieties. We'll have hydraulic power steering systems and that use a hydraulic pump, and then you have electric, which has become more common on modern vehicles to have an electric power steering system, but they're designed to reduce steering effort. Before we had our power steering systems like this, what you saw in cars is they had giant steering wheels to gain mechanical advantage, so that center of rotation gave them more leverage, right, with a big old steering wheel. Nowadays with power steering, they can have nice little bitty steering wheels because of the power steering system. But prior to power steering, you had strong arm steering and we had big steering wheels on these cars so that they could gain mechanical advantage. So this is a couple of pictures here. This shows the power steering gearbox that I was talking about here that you see on your parallelogram systems there. Power steering gearbox, Pitman arm, idle arm, center link, inner and outer tie rods. Then on your rack and pinion steering, super simple, still power steering on these, but then we add our hydraulic assist. And all they do is they have a piston on either case that they have they're directing hydraulic fluid to a chamber that helps move the steering either way. In this case, very simple with a piston. And a piston on this side would drive the rack this way. They switch the pressure and drive it back the other way. In a similar way, it helps them turn the gear in this gearbox system. This is one of the earlier designs. Ford takes the cake on this one. They are the ones that I know the earliest had power steering. They had it back in the late 50s, early 60s. That they used a hydraulic ram like you see on heavy equipment to help move their power steering system. Pretty ingenious for its day. Then we get to our stuff here with our electric. All they're using is an electric motor. So you see an electric motor system here. You can see your electric motor there. Little electric motor on your rack and pinion style there. One of the things to understand about the electric assist is this technology is really awesome, pretty cool stuff. This is what has enabled us to have cars that can park themselves and stuff like that. One of the things to understand about this is that in order for that system to be effective, it has to be calibrated to know where straight ahead is. And so in that regard, they'll have a steering angle sensor of some sort that is tracking the position of the steering wheel, so that it knows how far we've turned to the right or how far we've turned to the left, and knows exactly where it is and what the limits are of that system. If you ever have to do replacements of parts in these systems, you usually have to, at the very least, recalibrate where zero is in center of this car. Some of them are resettable and others are not, in that case, to where when you do an alignment on this car, then where it thinks straight ahead is where you have to align the car to, and so that you don't piss it off. So if you set, what I used to be able to do is set the steering wheel where I think it's straight ahead. Nowadays on these cars, you better set the steering wheel to where the steering angle sensor says it's straight ahead. And for some of these, like I say, you can recalibrate that steering angle sensor. Other cars you cannot. And for the cars that you cannot, then you better align it to where 0 is according to the steering angle sensor. Otherwise, you'll piss off that car and their electronic steering and stability control system. And like I say, super cool technology. The technology that's in play here is what allows us to have park assist. They add cameras to this now, and now you've got the computer that can watch and parallel park for you, or things of that nature. So really neat stuff. And even control lane, collision avoidance and lane guidance systems is all typically incorporated in with your electronic power steering. This is a separate PowerPoint, so when you're looking at this in Canvas, then make sure you go to the separate PowerPoint to refer to. It won't be in the other PowerPoint. And so I'm going to include this at the end of our steering suspension, so you'll see it in there. But refer to the other PowerPoint for this information. Want to talk about doing alignment. So doing an alignment, a lot of times the reasons for doing alignments that will have customers come in and complain of will range from bad tire wear, car pulling to the right or car pulling to the left, steering wheel being crooked. A lot of times people will want to realign their cars after they get a new set of tires because of what I talked about, that I said if once you start a bad wear pattern in a set of tires, it cannot be corrected. And so a lot of times to start out, people invest a lot of money in a set of tires. They want to make sure they get the best life out of those, so they'll do an alignment along with a new set of tires. So when we do an alignment, the first thing we have to do is a pre-alignment inspection. And so we want to make sure that all of our steering and suspension components are tight. As long as we don't have any worn parts, then you can move on to doing an alignment. Now, you can align cars that have bad tires. That part doesn't matter. They have severe wear or edge wear, things like that. I can still do an alignment on that car. What I cannot do is align cars at least properly when they have different size tires. So they have to be the same size tires, and at the very least on the axle that they're on, right? So I may have like bigger tires in the back and smaller tires in the front that would give the car a raked stance. That's fine. But I can't have a different size right to left, because what that would do to alignment machine is it would see that as the suspension sagging or something, and you would get improper alignment angles. But worn out tires, if they're all the same size, doesn't matter. I can do an alignment, because an alignment is based off of the steering and suspension geometry, not off of necessarily the tires itself. However, when you do an alignment, you want to make sure that the tires are all aired up to the proper pressure, don't have any worn parts. Then we're going to pull it onto an alignment machine once we've done our pre-alignment inspection that we'll be doing out in the shop with the lab activities that we're doing for this class. The pre-alignment inspection done, right? Air up all your tires to the proper pressure. Then you're going to go through and pull it onto an alignment machine, and it's going to go through a calibration or comping procedure, right? So typically what we do is we mount cameras, or not cameras, but targets on all four wheels. So then you mount all your targets, you go through a calibration procedure as prompted by the alignment machine. It's going to have you roll the car forward and have you stop. It'll take some readings. Roll the car backwards, have you stop at a certain point, take some readings. Roll it back to center where it was before. Then it'll do a caster sweep where you swing the wheels all the way out to a lock until it tells you to stop. It'll calibrate there. Swing it all the way the other way and calibrate there. Bring it back to center. Then you've got your angles that we would be looking at here. So the angles that will come up at that point, if you get through the calibration successfully, is the angles that you'll see that we measure in a typical alignment would be camber, caster, toe, steering axis inclination, and toe out on turns. One of the big takeaways that I want to make sure that you understand is that camber, toe, and toe on turns are the only angles that affect tire wear. So the angles that affect tire wear would be camber, toe, and toe on turns. And we'll look at those angles individually so that you understand that. But those are the only ones that affect the steering geometry. The tire wear, in this sense that they all relate to how the tire is positioned to the road, right? Is it square to the road? Is it tilted in or tilted out? any of those things would cause tire wear. Now, all of the angles that you see up there can cause a car to pull. It can cause a car to pull right, and it can cause a car to pull left, right, cause a crooked steering wheel. Every one of those angles that are up there on the board can cause issues with cars pulling right or left. But the only ones that cause tire wear issues are camber, toe, and toe-on turns. We'll talk about SAI more specifically, which one of these angles are typically adjustable, or they're all typically adjustable with the exception of toe-on turns. Yes, good enough. Really, SAI is not adjustable, but it's an angle that we look at for crash damage. Toe out on turns is not adjustable. It's pre-engineered from the factory. Typically, camber, caster, and toe are angles that we do adjust. I want to say a little bit more about the alignment. When you do an alignment, the angles that we typically can adjust, all right, or at least have the potential to have adjustment, would be caster, camber, and toe. SAI and toe-on turns not adjustable. When you do your alignment, you always start at the back of the car. So you do your rear axle first, and you aim your rear axle down the center line of the car, caster, camber, toe on the rear. Then you move to the front, and you align your front wheels to your rear wheels. And that's the way that will go. So looking at the angles that we have here, this is camber, is the tilt of the tires in or out. So it's tilting in or out like this on this plane. And so camber is a tire wear angle, so that would affect tire wear. Then toe, if you were to stand straight up and look at your toes, if you point your toes out, that's toe out. You point your toes in, that's toe in. That obviously would also cause tire wear because we would basically drag the tire down the road sideways if it wasn't aimed straight down the road. Now, caster is not a tire wear angle, but it can cause a car to pull. So where you've seen caster like this is, a lot of you thought you were super coordinated as a kid when you started riding a bike, and you're like, hey mom, look, no hands, right? Because the rate of the forks of your bike was like this. Positive caster forces and makes the tire want to go straight, or the wheel want to go straight. And so if you've ever noticed, when you get done completing a turn and you let the steering wheel go, a lot of times the steering wheel will return back to a straight position without you having to touch it. That's because of the positive caster that you have. And so in this case, the weight that is carried by the car, I'm going to position myself a little more like the picture, but the way is carried by the vehicle with caster pushes the tire out straight. So we're carrying the weight back behind the wheel, and it pushes that wheel out and makes it want to go straight. Very noticeable on bicycles and motorcycles, the angle of that caster. On a car, we would follow it from the upper strut mount down to the lower ball joint. That's the angle of caster. If we hang the weight out in front of the wheel, and now we're carrying the weight out in front of it, that's kind of like your shopping cart. And you know that when you get on that shopping cart and you point it towards your car and you ride it down the ramp from the supermarket, it always goes straight towards your car, right? Heck no. It goes wherever and follows whatever rut and dip and everything in the road. So caster's like your shopping cart wheel that is dragging back behind the cart. Really easy to turn, right? But will follow any which direction, and so not good for vehicle stability. So for cars, we usually want, a few degrees of positive caster, which would set that tire out straight and make it track easily down the road. Caster will not cause tire wear, but it can make a car pull. In the rule of thumb, something to write down about caster. I need to say this. Something to write down about caster. Because caster does not cause tire wear, but it can cause a pulling problem, we can use caster to correct for road crown. So the roads that we have, most roads are sloped from left to right, which if you set a car up with neutral caster where it had the same amount of caster right to left, then the road crown would push the car off to the right. All right. So because most road crown goes from the left down to the right and slopes off to the edge of the road to the right, then we usually compensate for that in our alignments by adding a little bit more caster to the right side of the car than the left. Half a degree to a degree more positive caster on the right side to the left. And so that's the rule of thumb that I would give you for doing alignments. Half a degree to a degree more positive caster on the right side than the left. because the rule of thumb is the car will always pull towards the side with the least positive caster. So in that case, if I had a perfectly flat road and I ended up having 2 degrees caster on the left and 1.5 degrees on the right, then that car would pull towards the right. If I had a flat, perfectly flat road, no road crown, and I had 2 degrees of caster on the right and 1.5 degrees of caster on the left, it would pull to the left. The reality is, usually about 0.5 degree to 1 degree more positive caster on the right than the left will make a car go straight down most roads that have a normal road crown that slopes from left to right. So that's good enough. Camber will also make cars pull, all right, and so will toe. So I'll say that also while you were doing look mom no hands, if you leaned your bike to the right or leaned it to the left, you could get it to turn, right? That is now camber. So camber will make it pull, and obviously toe would make it pull too. Then if I had this tire going straight and that tire towed in, then that would have more friction this way, and it would pull towards the side that had more friction in that regard. Same thing, if this one was straight and that was towed out, then it would pull towards this side because it would have more friction. So toe can make them pull as well. Camber would make cars pull. Caster can make cars pull if it's out of adjustment, but usually because caster doesn't affect tire wear, we use caster to correct for pulling problems when all the other alignment angles are fine. Bad tires, I should say too, will also make cars pull, so be careful about that. If all your alignment angles are cherry, they're perfect, they're where they're supposed to be, and you still have a car that pulls, that's when it has a radial pull and you do your little trick of what? Crossing the wheels to see if it's in the tires. So toe on turns. This one I want to always just make people aware of because this will cause tire wear, and this is not an adjustable angle. So the setting of the steering arms, which are attached to the knuckle, we see our little steering arms here, they're set up in such a way that when I turn it all the way to the locks, I get a little bit different degree, a tighter turn out of this wheel than I do out of that one. And that's set up in the steering geometry from the factory, and it's not an adjustable thing. If it's ever way off, then these are crash items, and sometimes they're serviceable that you can unbolt it and bolt a new one on. Other times you would have to buy the whole knuckle. So on the knuckle here that I have here, this would sit up and you would have a strut attached there, control arm there. This is your steering arm that's part of the knuckle. Sometimes it's serviceable and it's unbolted. We refer to it as a crash item because it doesn't have any parts that would wear out, and so the only way it gets damaged is if it was in a car crash. So, but this geometry is set up from the factory. It's not adjustable. And so, but what it does do, or what is important to understand about toe on turns is that the priority when you're making a U-turn or turning is not steering geometry anymore and tire wear. It is just making the turn. And so tire wear angles go out the window during turns. And so all that being said, want to make sure you understand, you always get bad tire wear during turns. And so if your habit is to make a lot of U-turns, then you should expect to see really crappy tire wear on your cars if you make a lot of U-turns. So if you live in a cul-de-sac where you make U-turns every day, or if you park on the right side of the road every day when you go to work and then you make a U-turn and go home, if you do that every day, you will ruin your freaking tires. And so what I tend to do religiously is instead of making U-turns on any of my cars, I set myself up and I make the block, right? And I do stuff like that, and then that will help you get better life out of your tires. And if you do make a lot of U-turns, then you better be freaking rotating your tires more often and stuff as well to try to keep it under control. But in the end, you're going to ruin a set of tires by making U-turns. And so I would have customers that would come in sometimes and complain of tire wear, that they had a lot of edge wear on their tires, and like, man, I don't know what's going on. I go and check it out, don't see any worn parts, go back, throw it on the alignment machine. The alignment numbers are cherry, and then I would realize, or I would have to come in and have a conversation with them about how they drive their car, because that's going to be the answer to why their tire wear is the way it is. If they don't make, their alignment angles are fine. I want to find out, do they live in the mountains? If they live in the mountains, you make turns all the time. Your tire wear is going to be crap. Do they do the park on the side of the road, make a U-turn, go home? Do they live in a cul-de-sac? And I would bring up those conversations and sneak up on them, because I didn't come in and say, oh, well, there's nothing wrong with your car, because people want you to do something to fix their car, right? But in this case, there's nothing to fix on the car. I have to fix the driver of the car. I need to change the way that they drive, their driving habits, and fix that to be able to fix that car. And so something to just consider in that regard. SAI, the last angle to talk about, this is just a crash angle here. It's a diagnostic angle that if I did a lot of work for body shops, and we did at the shop there, and so this was a diagnostic angle for us to be able to tell if something was bent. And so the general rule of thumb for SAI, it is a different type of geometry, and what we're looking at here is that we're looking at the angle now from the front, and you'll notice Caster was from the side, right? So SAI is now from the front, and what we're doing diagnostically as an angle is a imaginary line from the mounting point of the strut, or it could be the upper ball joint in some cases, down through the ball joint here. Similar to Caster, except Caster would be from the side. This is from the front of the vehicle. And then we compare that to true vertical, and it gives us a degree diagnostic angle. And how you will tell if a car is bent is if those angles for SAI are not the same side to side. Now, my rule of thumb for doing alignments for the body shops on cars that I know have been wrecked, if I was within a degree side to side of SAI, it's alignable. I can fix it. If I'm further off than about a degree, then we have to find what's bent. And so that's the case there. One other thing that I need to come back and touch on before we leave this lecture, and something that I'm adding to the other lecture from suspension and steering. So I want to talk about something I missed in this lecture in checking ball joints. So when you check a ball joint, we talked about load carrying and follower ball joints, but I didn't talk about checking ball joints, which I need to talk about now. You need to be able to identify how the weight is carried to unload a ball joint so that I can check it. So this one, if you remember, my load carrying ball joint was here and my follower was here. Now, what I need to do is take the weight off of that ball joint so that I can check and see if it's worn out. If I let the spring just spread, because I leave the wheels hanging on this one, I let the spring spread, then it'll just pull on the knuckle right here and put tension on these ball joints to where I can never feel if they're loose. So when you check this one, then you're going to lift it from the control arm here, and then that will then compress this spring and leave the wheel dangling out here. Then I can get a pry bar under the wheel and pry up and down and see if the ball joint is worn out. Now, the big thing I'll move on from here and we're going to come back to that idea. So now I've taken the weight off of that ball joint, and then I can check and see if these ball joints are worn out if I lift it from the control arm. I'll try to get it as close to the control arm or as underneath the spring as I can to help support that vehicle on that jack now and keep it balanced. On this one, if I lift the vehicle from the body of the car, then we're going to have the suspension swing down, and then all of that would be caged between this upper control arm and there, and then I would have no tension on the ball joints out here. I can pry up if I lift from the body, and then check the ball joints on this one. Now, I can check everything if I support it from the body on this design. But one of the things I want you to be careful about, and this is not in the book, is while I have this design supported from a jack over here, I'm isolating and I cannot check to see if that bushing is worn out while I have it lifted from a jack right here. I can check the ball joints, which I need to, but on this one, I would not be able to tell if that inner bushing is worn out while I have it supported from a jack on the control arm. That is a big deal because you may miss a worn part that's loose if you're checking it this way. When I was taught in school, they're like, yep, this design, you lift it from a jack here, this design, you leave it hanging. And I had to learn the hard way in the industry when I first had my first worn out bushing over here that I never found in my suspension inspection, and I couldn't figure out why I couldn't get the alignment machine to compensate. So this would be my rule for you. The really accurate way is to say, or very concise, is to say, this one I need to check both ways. I lift it from the control arm here so I can check the ball joints. I lift it from the body or the frame so that I can check all the other bushings. This one, if I just lift it from the body or the frame, I can check everything. However, if you have a hard time determining which one is your load carrying ball joint, which is your follower, it's a simple solution. Check them both ways. Every car you get, check it both ways. Lift it up in the air from the body, check everything, lift it from the control arm, check again. And if nothing's worn out and tight, then nothing's worn out and tight. The truth of that will be there'll be some cars that you didn't need to check it both ways and some that you did. But if you can't figure out the difference, don't worry about it. Check them all both ways. Good enough. So that's chapter 112. Out of your book, steering suspension. Make sure you do that. Watch these videos. Do your homework. We'll have an exam on this stuff.